So today it's a great pleasure to introduce to you Johan de Kleer. Johan and I go way back. He was the graduate advisor in my undergraduate dorm at MIT. And he taught me all about having a good time, like you go home in the evenings and you solve problems from Schwamm's outlines. Okay, very exciting time indeed. He's well known for having invented assumption-based truth maintenance systems, which is a lovely way of being able to keep track of your reasons for believing things, very powerful for diagnosis. And in fact, the general diagnostic engine, which he developed, is an algorithm that's like the baseline algorithm in the area and has been widely used in industry. So, and now he's been applying these ideas to design and thinking hard about what that means and how it should work. And without further ado, I give you Johan.
Well, you didn't tell any bad stories about me, so I won't tell any bad stories about you. Yeah. Some things better left lie. So thank you very much for inviting me. Talking about a little bit different topic than I have talked last time I was here. Last time was diagnosis. So you can hear me okay in the back? Okay. So design. So what is design? Now, Don Norman's not here. He has one thing of design. But what I mean by design is a plan for an artifact and a plan for constructing the artifact that, when constructed, performs a function. And I think that is a fascinating problem. I've been interested in that from time when I was a little kid playing with mechanical sets. How do you achieve some kind of function with these set of parts or whatever? And usually I never had enough parts, and I always had to convince my parents to buy more parts for me. And I've worked at that over the years. In fact, my PhD thesis was originally supposed to be on circuit design, but I spent a year on it, and it didn't work out. Then I did qualitative reasoning instead. So I think it's fascinating. It's something that's uniquely human. We've been doing that, for hundreds of thousands of years, inventing new mechanisms, new weapons. And I think it's very far. It's not something that's a knowledge problem. It's not something that's a data problem. It's not something Google's going to solve for you tomorrow or anytime soon. So I think it's I find it a fascinating problem. Okay, so let me delve into that a little bit. So let me give you some ways that I started to think about it. So this talk is not a complete talk in a sense. It's a complete talk, but it's not worked out completely. So feel free, I'm here for the next 2 days to go and fight with me about where I'm right or where I'm wrong. So I think of design as trying to achieve a desired behavior from a structure that needs to be constructed. That's a shorter way of saying what I said earlier. Now, the first insight I got from this, what I think were the key insights, I got this really from Vadim Shapiro and the people who did mechanical engineering. They view this as an inverse problem. So I'm going beyond computer science. I'm going to go beyond engineering. But let's say you want to design a circuit. This is insane, and I'll actually use the word insane in a second. If you have all possible graphs and all possible topologies, all possible components, all possible parameters for those components, if you choose something specific, then you get a behavior. I think this is really important, and Vadim has won me over. If you cannot lay out your design problem in some mathematical way, you got a problem. You don't really know what you're designing. And what's also interesting is, and I can't talk about this very much in my talk, is once you do this, you can start using some ideas. You can start seeing symmetry in groups, and you can start seeing Lie groups, and you can start seeing algebraic topology. There's a structure of this space. I won't talk about that today. But what I like about it is they can frame it as an inverse. What I like about it is they can say, okay, let's say I want to have a certain behavior, and I have these components and these parameters. What topology achieves it? So they're starting to have a language, and I'm adopting their language to now characterize search spaces, characterize the design space. And it's very critical that you're able to enumerate all your possible, describe all your designs and also enumerate them, usually from simple designs to complex designs. So you could say, Johan, what the heck do you know about design? You were always working on qualitative physics and ephemeral things, and yes, you thought about a year at MIT thinking about how to do circuit design, you couldn't figure that out. Well, in the last 10 years or so, I've been struck with 10 years. I've been head of a project, or co-head of at least the software and most of the hardware part of a project to design a new copier. I spent 5 or 6 years misspent in adaptive vehicle make. This is a DARPA slide, so I'll just show it to you, my experience, and I'll give you a few pieces of this. So in DARPA was trying to do, this is the slide that got, this is the next slide, got Palaramenko $600 million. It must be in his shoes, right? So on the horizontal axis, you see complexity. Vertical axis, you see how much time. And what he tried to do is plot, like VLSI is here. But what he's noticed for complex systems, the amount of time to develop a new product, which started to take decades. And the worst example, of course, is the Joint Strike Fighter. So, I'm not going to talk much about AVM, but many of the projects I'm going to describe came out of AVM. But what I got to do inside of that is we were teamed with BAE Systems, not the research, also the research people, but more interesting were the people who actually designed real combat systems. And that was an eye-opener and a half to understand how things are already done. I always thought, I get to interact with the Xerox design system, but I always think of, I work for Xerox, so they're totally screwed up. No, Xerox is completely normal. So I'll talk a little bit about that experience. And this was the second slide that he used. This is, most of you have taken engineering, know the standard V model. This is developed in the 1960s. This is you do some system layout, you do subsystem design, component design, you develop the components, you test see if they work or not. And so this is a very bad way to do design. It's actually, everybody has written papers on it. Very bad way to do design, but I can tell you in practice what people actually do. It's very hard. You start doing simulation. They draw all sorts of graphs. So, we don't have to test it physically. You can actually do a simulation, but then you still have to test it physically and discover it doesn't work. So what AVM was supposed to do is solve this problem. It failed miserably on that problem. I'm not going to talk about that, why it failed. Its failure is actually politically a disaster, I think, for research and design and manufacturing, because this $600 million failure, well, they were cut off at the knees at $400 million because the DARPA had changed. But also you have the design institutes that Obama set up, the NNMIs. You have one down the street here in Chicago. I go there quite often, the DMDII. Again, both not really being able to address design and manufacturing research. Anyways, that's a political comment. So let me see what I discovered. What I discovered, when you look at BAE, it is scary. It is scary. I don't know what you teach design here in this building, I suspect, but there's probably about greater than 2,000 tools that BAE uses. They had a corporate program of trying to reduce the number of tools they use. And the problem is very hard. There's so many different aspects of a design. I mean, you're probably familiar with the SolidWorks or the Dassault tool chain, and then you have the PTC, and then you have the PLMs, and then you have the multi-body analysis, and then you have to worry about armor, and then you have to do the meshing. So you want all these pieces to work. Let me tell you, they're not integrated. What designers do is spend a lot of time actually writing little Python scripts how to get the output of one to input to the other. So engineering is not how you see it in the marketing brochure from Dassault or PTC. And there are 4 key vendors. It's very important. I'll get back to this. PTC, Dassault, Siemens, ESI, and then there's the open source one we tried to develop in AVM, which failed. Model-based engineering is progressing extremely slowly. In fact, I see seminar announcements now that model-based engineering, what's next after model-based engineering? I'm telling you, they haven't even done model-based engineering yet. And there are no languages. The standards, they do things like SysML. They're not standard. In fact, one thing that really shocked me, since I can know most of you are in AI, is that most of mechanical engineering is actually now doing bad AI. I can say all these things. I'm standing here now, and you're not like DARPA audience that will yell at me at this point. So let's look a couple more slides before I delve into my fame of the world. So this is from NASA, and what's interesting about this is, and there's not very nice charts, and the graphic artist is confused about percent and fraction, but ignore that. What's interesting is that most of the cost of the life cycle of a design is done, most of that cost is incurred. Not that it's spent, this is the time effort, but choices you make here drive the rest. So whatever you can do, you're going to hear me, this talk and next time I'm going to hear is trying to push as much of that in that direction, or actually more of the effort so that the total cost goes down. All right. Now let me tell you something else, another way of looking at this. So what happens is you have 2,000 design tools that are being used to design your airplane. What you have is the design, it now becomes platform aware. And what I mean by that is the tools that you use to design that system, that airplane, it had a multi-body system, it partitioned the design at fissure lines, which may or may not be good for the design. And actually, to even be more human about it, it's also aware of the 1,000 engineers and how they were organized. So how can we get away from that? How can we look at much broader spectrum of possible designs for these teams of people that's not platform aware, and where the platforms that developed it are not implicitly embedded in the design itself. So briefly about this, what we'll notice right now is manufacturing technology is progressing at an enormous rate. Even the latest ones are all sorts of incredible new materials being formed. There are all sorts of additive manufacturing. And the tools, and though we may have a few algorithms, the tools are way behind what is possible today. Okay, now let me dive into my grungy details. This is my really high-level perspective of how design works. On the vertical axis, and I'm going to then hang my talk off these 4 slides. This is the structure of the system that you're designing. At the lowest level is the physical system. It actually is the world. Then you may have atomic structures. I don't know. I don't care exactly the level of detail. Maybe they're differential equations. Maybe they're macros. Maybe this level is qualitative. This level is maybe teleological. And what happens here is these are the structure abstractions, and these are the behavioral abstractions. So what you do is you do design. You may just, and what you see here, the structure space is dense. There's an enormous number of possible designs. Here is relatively sparse, comparatively speaking. So the goal of the design, remember, is to get a behavior from a structure. Now, how do you figure out the behavior of a structure? Well, the way I'm going to borrow a way, you want to say simulation. Simulation is such a narrow term. So I'm sure most of you heard Ken's talk. I use envisioning, because what you really want is you care about all the behaviors of the system, and do all the behaviors achieve the function that you desire. So design is the process of going from a desired behavior or properties of a desired behavior to a structure, and envisioning is the process of actually having instantiated a system and envisioning its behavior. And everything I'm going to say the rest of the talk goes around this. It's sort of a structure, search, planning problem. But let me go one more level of detail before I go. You think I'm insane because I'm going to say something insane. So I've been advocating at Park, and we're doing a few more of that, is just can you frame your design problem, whatever level of abstraction you want. I gave you that 3 cross products earlier, such that you can actually check. So can you actually search the space such that design will eventually show up? And let me tell you this, I'm not just talking about topological designs. I don't have time to talk about it. I'm talking about machining designs. I'm talking about additive manufacturing. I don't care. I'm talking about designing anything, not just discrete components, but additive and subtractive as well. So that's an insane designer. So I think part of what you have to get straight, I have to get straight, what is your design space? Second Second idea. What designers design, when I design, it's not just generate and test. I mean, that's ridiculous. That won't work. Might it work up at this level? But what you do instead is you look at what went wrong with the design. How does the particular design you came up with doesn't meet your behavior? So this is what I call the sane designer. I'm sure when I give a presentation at DARPA, I'm going to have to rename these, this insane and disane designer. So I'm going to talk more about the sane designer than anything else. Then the other thing you want, the other thing that's most designs that I've ever seen come from either an insane design being made sane or by analogy. Almost every, feedback control, the standard thing of an op-amp. The Greeks understood this in their water clocks, for example. It's being around. Almost everything is an analogy. Someone sitting right there who's an expert on analogy. I probably want Ken to help me there. I don't have much to say. I'd like to get started on that, but I don't have not much progress there. But I think it's absolutely fundamental. So let me talk a little bit about this level here, the qualitative level, is just to illustrate. Now, I'm not going to give you a talk on qualitative reasoning. Be careful. Basically, I'm going too slow, but I'm just going to stop when the time runs out. So qualitative reasoning, most of you know. I'm going to just summarize it for you. You might take qualitative values, for example, you take the equations of motion. Let's say they're ODEs. Just to make life simple, you can do this for PDEs. You can do this for topology as well. But so for ODEs, so you just take the sign of every variable, and now instead of writing the constituent equations of V equal IR, you write it in the qualitative terms. You may have landmarks below or above a threshold, and now you can define addition, you can define multiplication, you can define derivative, you can define higher derivatives, you can define integration, and you can define continuity. Now here it's a little bit different than Ken. My model is usually the real number line, so you have point, interval, point. So you have all sorts of rules that if you're 0 at a point and your derivative is positive at the next instant, that you will become plus. So this is qualitative reasoning. I'm not going to go through it really deeply. So the vision that we have, and we got to do some of this in AVM, is do the design in QR space. The advantage of QR, it's much more abstract, so the density of solutions is relatively low. So what we do is we try to determine just if qualitatively a design doesn't meet its behavior, and let me illustrate that in a second, how, then you know it couldn't possibly work. There's an example of where, it's a trivial example, where someone put a car, the car was almost finished, I heard this in AVM, until they discovered they had 1 forward gear and 4 reverse gears. So it got all the way through. We started to realize they got a bit wrong, and that was a little bit embarrassing. This is a trivial example, but QR will catch things like that, catch many other things. So here's envisioning. Let me give you envisioning in one slide. So here's a circuit. I'm sorry for the European resistors. We tend to use Modelica, which is European language. So if you have a battery here and a capacitor that's charging and another resistor here and a diode, and then what happens if you switch on the battery, then slowly this voltage rises till the LED diode turns on. If you were to do this with Modelica and you wanted to do all possible behaviors to figure out which ones might work, you're going to have to run an absolutely infinite number of simulations. These are just Modelica traces. So here is the case where the on voltage of the diode is 1.5 and the battery is 0.6. So what happens if you plot the voltage on the capacitor and the diode current, it never turns on, right? Because it never gets there. If you do it the other way around, the battery voltage is 1.5 and the on voltage is 0.6, then at a certain point, the diode turns on. These are, from your and my perspectives, these are the only two qualitatively distinct behaviors available in this system. This is the envisioning of it. What's the difference about envisioning, what's really critical in envisioning is not necessarily that it's qualitative, but it's multi-trajectory. So in one structure, you identify, oh, it will stay off, it increases in an asymptote. This is sort of this way. And this, the diode actually turns on, and then this will asymptote. This is it. Now, you're going to laugh at me. I don't know if this is real engineering faculty in here. This is a trivial system, a trivial circuit. I assure you, we can generalize this to thousands of components, which was the size that we had dealing with AVM. You know, qualitative reasoning might take you a couple of hours to analyze this thing. This is just one. I'm going to go back to this slide in a second. So this is an envisionment which is slightly more complicated. It has to do with, I think this one is about having a car going up the hill. I will show you it in more detail. In this envisionment, what we did is we marked, this is the start state. Red are failure states. Those are states that do not meet the requirements of the designer. And yellow is the path that you're trying to get through it. So from this alone, from this qualitative reasoner alone, from this envisionment, you can tell that there is a path to a solution from this to green. And that alone, now you get many designs, and like, for example, that car that couldn't go in reverse, but is where you find out there's no path at all. And when there's no path at all, you know that design couldn't work, and there's no even reason to fiddle with the topology or look at the sizing of components because it just won't work. Most topologies will not achieve what you want. Okay, I'm going to get back to that in a second. Let me skip forward. So there might be other ways of describing components. And here's one that we have used in the past. You're probably very familiar with it. This is one we used in copiers. So most high-end current copiers of Xerox, I'm talking about the high-end, one that looks about this big, use our model-based technology to do internal scheduling and internal operations. And they literally have something very similar to planning domain description language, which you're probably very familiar with here. This is all simple predicate calculus. So, but you can do design now at this level and design a machine, and then, so now it actually becomes much more reasonable or even plausible to have an insane designer at this level. All right, let me go to the next piece. Boy, let me talk about the sane designer. I think the sane designer is a designer that looks at what went wrong and looks back at how to change the design. So let's talk about that at a higher level. So the thing I've often wondered about is why are our designs so complicated? Why are they so many moving pieces in them? Why are they so hard to understand? I figured that there's an answer, actually. Is that we grasp some of that, maybe there are things, we have some principles about things might be easier to design. It might be, our tools might be better. It's easier to do diagnosis, and it's easier to operate. Here's the answer. I know the answer. This one I figured out. The question, the reason designs are so complicated is simply that the components that we build from, the ideal components don't exist. You can write a battery in a circuit and say, this is its capacity, and then this iPhone will work all day. But good luck finding a battery that fits into your iPhone that will last days at end when you're doing GPS. And the same thing is for cars or engines. Why does a car have a transmission? A car has a transmission because the torque speed curve for an engine is not linear at all. It's very nonlinear, and your transmission is trying to always trying to allow you to match the speed of the engine to the speed of the road, and then you get more efficiency. But again, it's because there's no ideal engine. Now you have this curse. And why do some race cars, for example, have both electric and fuel gasoline propulsion? Because the torque of a gasoline engine is 0 at 0 RPM, and the torque of an electric engine is maximum at 0 RPM. So, being a circuit person, I like this example. But let's say you can get a real good op-amp. Well, it might be designed for it. But guess what? It has all sorts of frequency problems. You can't get constant gain. So what happens is op-amps get more complicated. So this is a figure basic op-amp, and here is a 741 op-amp, which you've seen before, well, I've seen before. It is like 40 years old. Most of the components in this op-amps are kludges and patches to correct for why a simple op-amp won't work. So I think that patching and what I call sane design is probably what designers do most of their time. So here's a plot of a slide I showed here before. It's called model-based diagnosis. Model-based diagnosis is a way of identifying why some system is not working as intended. So if you have an actual system, you can observe some behavior. You have a model of the system, and you can predict the behavior. Then you get a discrepancy between behaviors, and then you're trying to reason backwards from the discrepancy to what caused the problem, and then you replace that component. You also do a little bit of that. I stole that chart from a different talk, but you might also look at what other consequences of that fault are and see if that's consistent with your observations. Now, the thing you say, what's the connection? Well, notice that this graph is symmetric. So the problem of finding out what is wrong is, think about it, is actually finding out how did this system change so that all the observations I see are consistent. So what you can actually do, and what we do, is you can take an old design, and it has predicted behavior and desired behavior. And what you do now is you look at how did the model change to get the desired behavior, how to change the model. So that's a hard concept, but it's a very powerful concept, because I think it's fundamental to design practice. Well, I showed this 6 years ago, but here's a full adder. So it's supposed to add 3 bits, A, B, and a carry in. And its output is lower bit and the carry out. This is the circuit. You can trust me. This is the correct one. So let's say you have 0, 1, 1. And of course, 1 and 1, you know the answer. It's 1 and 1 is 2. So in binary, that's 0 for the bottom bit. And oops. So let's say you get 0 here. There's something wrong. And now you can look back, and this is what model-based diagnosis does, and I'm not going to explain it to you. It looks back in a very systematic way about which components can contribute to it. And it will notice that A2 can't do anything. Well, anyway, it has nothing can be here, and it will quickly isolate the fault to these 2 components. And what it says is, well, maybe this is shorted at 0. But hey, it can also, and it does actually do it, it could actually, maybe this is really an AND gate, and you made a mistake and you put an AND gate in there. That would be consistent with your observations. So let's just change that problem into its reverse. Let's say it was an AND gate in there, and this is a failed fault adder, and then you get the same results. What it will tell you is that maybe this A3 is an OR gate. So I just gave you, so here is where our model-based diagnosis gives you a way of changing a design such that it's now consistent with your observations. Now you could be thinking in your head, well, what about all the other inputs and outputs? Well, before I say that, let me just say, so the idea is you have a design, and it sort of works, and what you want it to do, you want to make some minimal perturbation to it, and then you want to get a design that now works better. It's sort of funny, I was explaining this to I bicycle with a VLSI designer for NVIDIA, so I always bounce this up. He said to me on Thursday, he said, well, hey, so you can give me I can just do sloppy designs, and your software will fix them for me. And I said, yeah, you got it. Now, we've been talking to him for 40 years. Steve Purcell, you even know him. So let me talk a little bit briefly. I'm not going to depth. I'm actually just explaining to you that I'm not an idiot, is that there's lots of other inputs and outputs. So what you do is you want to preserve what's worked in the past or other things that have worked, and you want to modify it such that you only change what changes the thing that you didn't want. GDE already does this. So even the thing 20 years ago, it never realized till recently that this was valuable. But it will figure out, because what happens is if you have multiple time ticks for a circuit like this, it will take the previous times into account under one assumption, which is that things are not intermittent. So you have to have a different issue. And I don't want to do this. So I don't want to push further on this, but what's nice about a model-based diagnosis is it generalizes to higher cardinalities as well. So if combinations of components. We also can do this for topological changes. But there's a limit. I mean, after a while, the sane designer becomes insane. But I want to point you, so this approach works. So I want to give you a couple more things. I want to talk about this part. So just because you got a design at one level, and you got a design, doesn't mean you're done. Because you have something in this abstract space. You need to get it into a greater level of detail. And I sometimes call this function to structure. Not quite the right word, but it's moving from one structural abstraction to another. So here is again where qualitative reasoning works, comes to the rescue. So when you measured, this is the circuit, same circuit I showed earlier, this time in the US symbols. This is the envisionment for it. What you discovered that here, this envisionment, there was an ambiguity generated here. So in this particular case, and many cases, unfortunately not all cases, the envisionment can directly tell you that what only matters here is whether VBAT is greater than on V. So what it tells you is when you go from the structure, from the qualitative model to a more detailed numerical model, it'll give you a criteria on the quantities which are needed to be fulfilled for this to work qualitatively. This is again, so this is a tool we actually built for an AVM. Here's an example. I'll go in a little more detail. Here's an example of where you have a tank that's going up a hill, and you have to shift it into gear, and there's a requirement you can't roll back that far. Well, here's a more numerical simulation of it. So this is the position. So red is the position, velocity is blue. And what you're trying to do is it rolls back a little bit here, and I can map one for one the qualitative states here to the positions here. So again, this tells you if when you design this brake system or this engagement, it's actually an engagement, how you engage the clutch. There's always a little slop. It tells you if you want to make these, if you want to be preserved here, so these are no ambiguity, but here you have an ambiguity very early on. You have three possible ambiguity. It'll start telling you what conditions need to be true such that you will stay on that qualitative pattern. All right. I'm doing okay on time, actually, better than I thought. So now the next question you ask is, what the heck am I going to represent this stuff in? Now, I used to always think of, oh, well, let's do predicate calculus or QR, but I think that's too limiting. So I'm going back to algebraic ideas from algebraic topology, which I'm not going to explain in much depth at all. But I think that's the most general representation. There are papers now how what's really nice about it, you can represent circuits, you can represent any lump parameter systems, you can do cell complexes, you can do partial differential equations, you can do geometry. And so it's really attractive to me how to get this unification working. And you can start, we have compositionality and composability. We define them in our modeling techniques, and you can talk about compositionality is that you can construct the behavior of a system from the behaviors of its parts. Composability is when you put parts together, they actually don't somehow change each other's behavior. These things can now be mathematically characterized in category theory. I just finished a talk on that, a paper on this. I'm going the wrong way. I'm not going to show you the paper, but here's an example. We're actually using sheaves. If you're familiar with category theory, we're using sheaves to do all this. And we have an initial, very, very initial prototype implementation. Look, I'm trying to go for before you think I'm crazy, I'm trying to go for the big thing. I'm trying to get a really general way of looking at design that actually, not just theoretical, but actually works. Now, just to show you, and I'm going to change topics for slightly, is I'm not an idiot. You want to design something, but if it's not reliable, or it's not manufacturable, or it's not adaptable, or it's not resilient, it's also useless. There's not just one metric. And some of those metrics you have to think a little bit more about, and everything is stochastic, and we do incorporate that in our AVM projects. I just want to give you a really brief. So what we have done is we moved reliability all the way to the front of the process, because reliability in most corporations is done at the tail end, and that what happens is then you have extreme costs. You have the airbag problem. And I don't know how many we can catch those, but there were the airbag problems, battery problems on the 787s. We would hope that more analysis of reliability early on could point things into a better design space. So what we do, I'm not going to go through this slide, but what we do is very simple, is we not just have models of good behavior, we have models of faulty behavior. And then we have probability distributions on those behavior. That means once you can very early on in the design cycle give you the probability of something failing or succeeding. And what we can do there is not just better reliability, but this is actually a design problem. The design problem is, what is the goal of your research? The goal of the design. What you want is, what General Motors might want to do is reduce its warranty cost. But once you start knowing reliability figures, you now can predict warranty costs. And if I use this engine or that engine, then you're going to have a different warranty cost. And believe it or not, this I could talk about for an hour, which I'm not, but this is actually one of the things that's being sold as we speak. This is actually something that's worth money today. So this is actually going into, I can't mention the name of the company, and the reality of having to do these things with industry is that you have to plug into someone else's design chain. You cannot just have a self-standing tool and expect to load in a model and give the output analysis. That will not sell. What people want is something that they have a tool, they have a model, and they can input that model literally into our tool. So our QR system doesn't use QPT. You take it a raw Modelica model. This analysis right now takes a raw Modelica model. You talk about how bad Modelica is, but we have no choice. Sometimes we have to clean up the models to remove stupidity out of models. Most people don't know how to write models, but that's a whole other talk. So this actually went to beta in AVM. We were actually able to have real designers use this for a drive chain and gave us lots of feedback. A lot of it bad. A lot of it, they wanted these kind of interface. This is not our interface, this is their interface. In fact, at one time you could actually log into this website and do it yourself. So let me talk about something else in the last few minutes that's very related to design. More and more, when you talk to people, when you talk to defense departments, is the thing itself that you're designing has to redesign itself. You want so for example, we built this. This is not a good example. This is a printer that we helped design. Actually, we did the software for that, but there's a successor which we helped design, and it's made out of different modules. Actually, this is it. What am I saying? What happens is this thing can reconfigure. So this is a never-down printer. If it jams, it reroutes the paper along someplace else. It more than reroutes, it reconfigures itself. If one of the printers jams, it'll go someplace else. And what happens is the customer never knows. The job will be corrected. If you're missing the odd pages, it will stack them someplace else and slip in the odd pages that are missing. So this is very successful. I discovered these things are expensive. This is probably I spent $15 million on this machine. So what we want to do is we want systems that can adapt to their situation. They can self-adjust as the task requires. And many things you can do. There's two ways to go. You get more functionality, But you also get part of the motivation of Xerox is once you have something that self-adapt, you can build that out of crappy components. And it fail more often because then the software will, whatever you want to do, you want a cheaper machine to manufacture or you want more reliability and uptime. So how are we going to design the designer? Let me just go to the next slide. So here's a picture that I have. I was redrawing this in Ken's office, didn't finish. But this copier that I produced, hey, it's still the same idea. It's mostly a sane redesigner. What it takes is there's the system itself. There's the model of the system. Of course, the system deviates from its model, so diagnosis is supposed to figuring out how the system is deviated from its ideal model. This then goes into the planner, which is maybe for our talk, we talk about it as a designer. And what happens is it readjusts the system. Now, there's something that's not here, but would have to be in any sane designer that's embedded, is you actually want to take active measurements on yourself to determine what might be wrong. You might have some ambiguity in your so the sane designer might give a human back some alternatives to fix. That's not good enough for if you actually have to be embedded in the system yourself. So you have to gather more information about yourself. Now, this raises all sorts of questions about what's the design. How do you design a system that's going to be driven by a designer that's embedded in it? How many different kind of modules? What level of abstraction boundaries there are going to be? Your design tools. And the question that often comes up more with DARPA than here is if you have a goal like this, they always worry about self-awareness and Skynet and anything that can adjust itself for evil. My answer, I don't have a great answer, but basically evil comes from whatever task you assigned it. Anyway, so there's a lot of other things going on. There's smart materials. We do a lot of work on smart materials, and those will feed into it too. For example, this happens to be a DARPA project we have right now. What we do here is think of xerography as printing on paper, or let's think of xerography printing a machine. So we take bits of machine and we basically assemble one-off machines one at a time, and we can do both different materials. We can do electronics. We're trying to get things like a wing, printing pieces of a wing, which has both actuation in it and electronics. So now we're talking about worlds in which, we have a couple different ways of how a system can redesign itself. You can redesign yourself with modules, like the printer or the snake of Mark-IM. So the snake of Mark-IM, what it will do is it will reconfigure itself. It has to go through a hole. It will go into like that. Or if it needs to walk over something, it will turn into a spider. Now the problem, when I say it will turn into, it's physically capable of being that, but the actual decision, right, this Mark-IM did this a number of years ago, is by a human. But I'm into this world where the designer has to be in the design. I'd love to work more with you, Mark-IM, about how it will decide when it should be a snake and when it should be a spider. So I think of these systems, and when I talk to DARPA, I use this term cognitive physical systems, because what would, I don't know, I'm pandering to DARPA, but you want something that, you want the same mechanism designed by the same materials to be a vertical takeoff, to reconfigure itself for speed, and reconfigure itself for stealth, reconfigure itself for economic, and that these are not things that I programmed in ahead of time. These are such that if there's a new context or a new situation or a new strategic world perspective that you have to deal with, that the system and the design, or in the design, can adapt to that. And I think the same, I'm not so sure about this yet, but because I haven't actually even built a prototype, but I think something like this is you need to know your own state, and you need to replan or redesign yourself. I think it's going to require more than is in this picture. It's going to have a little bit of the insane designer in it. But I think this is the right way. Let me talk about the final thing. Just this is my kicking DARPA in the teeth a little bit. Is that once you think of the design or in design, this whole thing between design software and system software is a distinction that is largely irrelevant and not very useful. The question is how to think about that. I used to have a little picture of soup here. They didn't like that picture, so I took it off. But we all like to build these little boundaries. It's part of our engineering training. If we can build a boundary for something, then we have exponential gain because we can solve each one individually. I'm just saying, I think this distinction between system and design is one that gets you into a lot of trouble once you want to put the designer inside the design. Last comment is another thing you're trained here is black box abstraction. You want to have a box that, okay, this computes factorial, or this box is a PID controller, and then not think about it anymore and build bigger level modules. I think that's also not very productive, and it's something I think we should examine more. Why? What good does it really do you? Black box abstraction is also evilness associated. When you especially notice this whenever you do anything about diagnosis, is a diagnostician has to look inside the abstractions all the time. So black box abstractions are actually something that undermines diagnosis and design in the designer in the design. Now the last comment I'm going to make, I'm actually going to be on time, is I'm not stupid. Designer, Don Norman is not here, but there's people and there's machines. And how that boundary goes, I have no clue. Now they interact in many ways. I should say I have a lot of clue, but I'm not going to talk about today. Interact in many ways. There's many people here, right? There's the designers. There's the people who constructed the system. There's the people who use the system. There's the people who get shot by the system or whatever it is. So there's many kind of interactions. But I know one thing that this thing isn't built of. The first thing that you're going to taught in engineering is that these are requirements. And I think requirements are a really bad idea. And I've even noticed that the BAE people is what has to go across this boundary is intent. I don't know how to express intent, but I watched that in BAE. So I'll give you an example that really brought home to me. So the Bradley fighting vehicle, which it's now out of production, but had a requirement on the door. So there's a door that opens where the soldiers run out. And it had to support 2 people running out. Now, if you look at all the videos from Marines, yeah, if you're being shot at, are you going to wait for your second person to get off the door before you run in? Because usually they have like a platoon or five or six people in it. No, they all run off at the same time. And any video you see from the recruiting video has 5 of them running out all at the same time. The BA engineers knew that even though the requirement was 2 people, that was nonsense. They knew it had to support 5 people, and they designed it that way. So when they get a bunch of requirements, the first thing that the BAE people do is they invert the requirements to figure out what were the politicians / military people thinking, what was their intent. And then they try to instantiate that intent in the machines. Now there are requirements like it shouldn't weigh more than 60 tons and it should stop in so many seconds. But many of the requirements really come from how the thing is actually going to be used. Now the last comment, I got time for questions. I'm not alone in this. These are the usual cast of my cast of characters I'm working with, and many of them work intimately. So I'm not the only person who does all this stuff. To a large part, I kick them around, trying to get them money so they keep on working. Vadim is at the university at Madison. I'm doing more and more work with him. Sai is graduated from Vadim. So that's it. Questions? I didn't get a single rock thrown at me. Okay, your turn. Pardon? Yeah. Yes, that's one part of what I'm saying. That's the same designer.
Right. So, on the other hand, every now and then we get lucky, and things get put something into a design that actually ends up talking about synergy and logic.
Yeah.
But sometimes actually you get lucky, put something in, and it actually does. It interacts with something else in a way you didn't understand, and it actually does better than you expected it to do. Right. So I didn't see how to grab that opportunity. When the sort of components have interactions that turn out to be useful in ways that you didn't anticipate. You put them in there to solve certain problems, and they actually have capacities that actually allow us to solve other aspects of the problem that were not really
Well, first of all, I think in my framework, it would notice that, and it would it would at least notice it was lucky. The question is whether it would remember that lucky idea for the next design. Insulation. Yeah, no, it makes perfect sense. I don't have it completely solved, all right? But that said, the topologic, what I meant by topological, is someone, I mean, another example was the Zumwalt, right? This new littoral, right? Somebody forgot to put oil in the gearbox or something, right? And the whole thing ground to dust. That's the kind of for me, that's a topological fault. And we don't have that as well, but for circuits, I do have that worked out where things can short to each other that you didn't, so the new connections can be there that you didn't, the same designer, pardon me, the GDE, the diagnoser, can hypothesize that there are extra wires in this system. So that. But that's a trivial answer. I'm sorry, I should have said that first. But the trouble is that requires n factorial. So you have to be something smarter than that. Right. Ken?
Do any of these designers do anything to help them reuse old designs? Do they have ways of looking at their stuff online? Do they have paper? I mean, do you ever see or do they start from scratch? Surely not.
As far as I can tell, no one starts from scratch. What do they do? I wish I should have a better answer, and I don't. I know that one of the really key designers did something which is the most insane thing I'd ever seen before, but it was a design space exploration tool just written for specifically for combat vehicles. And he would say, well, is there two wheel? Is it a wheel or is it tracked? But then that was his way of trying to explore the space. Now, I wish I had more to say. I can tell you one thing I learned from BAE is that the software people and the hardware people hate each other. You remember this too? The hardware people think they can do everything in hardware, and the software people think they can do, except the control systems, which they can do with their Simulink. And the software people think that they control everything, and the hardware people just doing physical objects, and the hardware people call the. I've heard, literally speaking, Paul Aramenko saying, those are just code monkeys. Code monkeys. You should have heard that too. So that's a fissure. So that's a fissure in the organization that's having an impact on our systems, big time. And also, the software people often don't have a clue. I mean, it's like I was telling you at lunch. I was giving a talk to some in Japan about, we'll see how many people pass here. I wrote, okay, This is software people, okay, who understands this? The state equations formulation of an ODE? Well, the software people don't know shit. They don't know the thing they're controlling. What? Yeah, it was funny talk. The next stage, I was going to explain Kalman filters to them, which are a really good idea. They were invented for tracking Soviet missiles coming over it, but they're really good at tracking when something is starting to fail, how to track the crack in the plate, or how to crack the wear of a bearing. Is a Kalman filter is the standard thing you would use. And anyway, I didn't explain Kalman filter to them. I want the same designer. I want you to be able to write down your design space. Okay. That's what I'm trying to capture in the same design. If you can't do that, then I'm not going to listen to you very well.
So it's a very interesting idea of applying diagnosis to the design itself,
yeah.
rather than just to an artifact.
Right.
That's very cool. But what I don't understand is, to what extent does that address the problem of complexity, of creating, you showed the 741 op and have all the little
Yeah.
tweaks and everything to make it actually work. Does the idea of applying diagnosis to the design, does that actually address this problem of accumulating complexity?
Is that enough? So I don't know. I mean, I can go further than you might first think. I can do higher cardinalities, but at some point, if you give me a blank circuit and say, okay, give me a half adder, well, it turns out I probably could do it. Okay, because I would switch into same designer mode and get it. But for the op-amp, probably never get there. So maybe there's something missing. And the thing I think one piece is missing, and answer your question too, is when you should be a library of analogies, and and the analogies aren't just circuits. All right, pardon me. They are, if you want to stabilize the behavior of some system, use feedback. And maybe the pardon? Right. And sometimes, and then there's the other really, really key idea of PID controller, which nobody knows here, but you feedback something, the signal itself, you feedback the integral of the signal, or do you want to feedback the derivative? And each one of them has different consequences for what can be done. In fact, what's nice about PID controllers is that qualitative reasoning is powerful enough to analyze PID controllers. So I would hope that when you get lucky and discover something, that something adds that to the library of analogies or strategies. Okay. I confused you. Oh. Yeah, I agree.
So does some of this, is there any way to actually use the complexity because it comes from multiple concerns, being able to report stuff across domains, help designers in your neighboring areas improve things at the same time?
Yeah, I'm all for it. I guess I'm agree. I don't know. I haven't thought enough about analogy. Right? That's something you and I should talk about the next couple of days. There's the other thing you haven't mentioned, that Ken and I have been kicking this all around for 20 years, is that look how powerful diagnosis is. The diagnosis could be done on your mind, right? Or the rules that you have. So now you got the problem is you got something in your system, the thing that's built on fire, whether companions. Then you have the problem that this came out this went wrong, I can do an analysis, maybe identifying what beliefs you had that caused you to. But then you got the next problem that I didn't talk much about. Then you better forward propagate that change and see whether it doesn't affect other things, undermine other things that you liked. Yes. If you look at the Wikipedia and the PID controller, you will find it'll tell you which things it's called tuning, parameter tuning. It will tell you basically what kind of problem you should do what. They probably teach it in this building, but not to you guys. Next one over. Which? Yeah, yes. Over damping, under damping.
But I'm saying that's a really, you know that you want something more stable. Like my first thought is slow it down. You know, like my first thinking, whenever I have a situation I feel like it's out of control, is I want to slow it down. That has a lot of virtues. It gives me more time to think about what I should be doing. It gives me more time. You know, things that kind of damp the situation tend to be good if you look like they're oscillating together. That strikes me as a very general idea. It could show up in a lot of different parameters in this thing to make it work right. I think it's pretty commonsensical. I think people think about it in their social lives as well as in their political lives, or in their as well as in running a haptic interface where it's getting some kind of weird oscillation. So I'm thinking, what's the status of those? What's the status of an idea like that, like damping? It strikes me as a really
Well, there's okay. I mean, I'd love to do that work. I mean, give me time, I'll address it. But it's interesting. Engineering does have pseudo solution to this, right? If you damping, well, if the poles and zeros better be all on the left-hand half plane, or else your oscillations have a chance of. This guy, he's a psychologist and he understands engineering. Oh, what are you? Oh, that explains everything. And it's also, would they look at, would engineering look at the eigenvalues, are they for this different kind of problem, but stability, but, all want to be inside of the unit circle. But what's nice about those, each one of those, I think, captures something very powerful at a more qualitative level. And I have a slide I didn't show. I think qualitative reasoning, as Ken and I have defined, is very limiting. I mean, it's limited. There's much more there. There is a space between what we can formalize now in QR and an equation. That space, someone needs to populate. Maybe some grad student in this room can solve this.
Okay, well, thank you again.
Okay.